we are now going to discuss of the vertical sections of those that type of phase diagram which I have just discussed in the last class. So, to remind you again, I am actually discussing a generic phase diagram in which two binaries forms eutectic and one of the binaries form isomorphous type of phase diagrams. The space model I have discussed with you already. Now, I am going to talk about vertical sections, then followed by isotomal sections, and then finally solidification if time permits. As you know, vertical sections are basically sections taken along the vertical direction, that is on the z directions. The way we take vertical sections are basically normally two. One is from one of the ends of the Gibbs triangle to the opposite side, thus like Bx or Xp. Other one is a line parallel to one of the sides. Here I have drawn a line parallel to AB side, which is Yz, correct. So, now let us look at it here, try to concentrate on this diagram. This is your ternary space model, okay. The solid lines, okay, solid lines and the solid even dotted lines which are very thick, they are actually part of these ternary things, okay. In fact, you can clearly see here how the alpha beta phase field looks like very nicely, you can see here, right. You have to imagine little bit. Now, I am taking as vertical sections along Bx. So, I take a basically a rectangle along Bx and cut the whole phase diagram. So, what I will do? I will cut it along this, along that, this, okay. So, you have alpha, this is the alpha, then you have alpha plus liquid, because liquid is the top, then this part is alpha plus beta plus liquid, and this particular section is beta plus liquid and beta. Right side is very easy to understand, because you are supposed to, you know the binaries very well. So, right side is easy to understand. So, you have beta and beta plus liquid is there on the right side, but on the left side what we have is alpha, that is also easy to understand, but alpha plus liquid and beta plus alpha plus liquid is what is difficult to conceive two-dimensionally from the three-dimensional picture. See, basically it comes because you have a three-phase equilibrium at the center or inside the ternary triangle, and that will be a triangular shape, and that is what is a triangular shape, you can see here. So, that is what you should remember. The triangular shapes of the three-phase equilibrium will remain in whether vertical sections or isotomal sections are drawn, correct. This is the first important conclusion, difference between the vertical sections we have drawn for the isomorphous system. For the isomorphous system, we have basically a lens or a cut lens on the both ends, that is what, but here it is not that, it is completely different. The next one, let us see. Instead of that, if I take a vertical sections along Yz, which is a line parallel to on the sides of the Gibbs triangle, that is AB, what I do, I take a vertical rectangle and cut the phase diagram. If I do that, you can clearly see if I cut, it will look like this, it is like that, you generate alpha, the alpha plus liquid, and here you generate beta plus liquid. No, because it does not cut the beta, so why there will be beta phase, and in the center you have a triangle called alpha plus beta plus liquid. Remember, here you cannot draw tile lines, I told you, right, you cannot draw tile lines in the vertical sections, because they are not connecting the two phase boundaries of the two phases or three phases, boundaries of two phases basically not connecting, very simple. But one thing you have to remember very clearly, even though it is a vertical sections, you see from two phase we go to three phase, single phase to two phase to three phase, this is how the transformation happens, single phase to two phase to three phase. At the bottom we have a two phase regions, okay. In fact, this one is more interesting, you have single, two, single, single, three, double, single, double, triple, single, single, double and single phase regions, okay. That is how it looks like. So, this is not difficult, right, this is not really difficult to understand. Now, let us look at the isotomal sections. So, the way we draw isotomal sections are like that, actually let me just draw it on the board, then I will come back to these things. I will draw it at 6 different temperatures, and it is important that you also practice along with me. So, I remove this part I draw the isothermal sections. In fact, I draw it on the board because this is much easier than drawing the vertical sections. So, we will take isothermal sections at very high temperature, suppose T1. I am just drawing the temperatures T1, and this is again T2, T3, T4, T5 and T6. What we do normally, we take a triangle which is same as horizontal triangle and put at each temperature. Wherever the triangle will cut, this space model we draw. So, obviously at T1 is very easy, T1 is very easy. T1 will have only beta and beta plus liquid, because beta B has the highest melting temperature. You can see here B has the highest melting temperature, B, Tb. Okay. So, therefore, this will be beta, and then we have a very small zone liquid plus beta, largest beta. This is the section at T1. I told you this is very easy, I do not need to discuss in detail. This is at T2, temperature T2. This is distinctly different. Why? Because you are not only cutting B, this surface of liquidous surface, but also this side of liquidous surface. So, this will be leading to alpha also. C has the lowest melting temperature out of the 3 components, and as you know, once you have single phase, you will have liquid plus beta. Similarly, you will have alpha plus beta liquid. The portion which is C rich, we have lot of liquid, that is what it tells you, correct. So, let me just draw the next one here at T3. At T3, you are not only, you are going to cut even the ternary section, because you can see here T3 is almost below the eutectic point of U1, below the U1 actually. So, because of that it will cut the ternary sections, that is why the complex, that is why the things will come. But what will happen, it will have, because it is lower than this, so it will have a large alpha zone, alpha extended, you will have beta, and obviously you will have alpha plus beta also. This is alpha plus beta. And finally, you are going to have a triangular alpha plus beta plus liquid and liquid will remain, still liquid will remain, because you are above E2. So, liquid will be there, right, because the liquid will be there till E2, below E2 there will be no liquid, because E2 is the lowest melting eutectic out of these two. So, that is how this section will look like. So, what we have? We have a large alpha, as you see here, if you cut it T3, we will have a large alpha zone. This is what you see here, this thing is almost similar to that, but little bit smaller. And you also have alpha plus beta, because you have this alpha beta thing will be represent, and you have a beta at the end corner, this corner, and then 3 phase region followed by the liquid alpha plus L, beta plus L. This is at T3. Now, what happens at T4? At T4, you will have similar things, only thing change will be change will be only that this region alpha plus beta plus liquid will be less prominent, alpha will be more extended, more amount of alpha will be formed, and you have large zone of alpha plus beta, alpha plus beta, beta solid is more. On the other hand, liquid is slowly vanishing, but if you clearly see liquid is remaining on the binary B and C, okay, and penetrating into the ternary, correct. That is what another important aspect, because this is the lowest melting eutectic sitting on the BC side. So, that is the triangular region is 3-phase zone, triangular region is 3-phase zone. You can see this triangle actually getting slowly smaller. So, that is you go down the temperature, this will be becoming smaller and smaller. Next one is T5. T5 will have large chunk of alpha almost, and beta will be small. Beta is small because beta zone is small here, you can see here beta is basically small. Solid solubility of beta, A and C solubility in B when the beta phase is very small, that is why. And then you have basically a small zone of liquid, ternary phase, a 3-phase zone is also small. T5 is also sitting above the E2. So, therefore, there will be liquid, but liquid is very small. This is what is the liquid, okay, very small, very small. You can see the liquid thing is slowly reducing. So, T6 is one again very easy. At T6 it is below the E2. So, therefore, everything is solidified. So, what we will have is basically a large portion of alpha, small beta, and alpha plus beta. This has more similarity with this T6 and T5, T1 has similarities. So, that is how actually this what do I say, this isonormal sections will looks like. You have to although I am doing it very fast, quite fast, you can actually imagine, you can sit in front of this 3D space model and imagine. But one thing is common in all these pictures, the ternary phase zone, sorry 3-phase zone alpha plus beta plus liquid remains a triangle. This triangle has 3 corners, you can see here one sitting as alpha, one sitting as liquid, one sitting as beta. Similarly, here also one sitting on alpha, one sitting on beta, one sitting on liquid, one sitting on alpha, beta and liquid. That is obvious, because so therefore, I can actually draw here again tie lines between the binaries. In the binaries you can draw tie lines very easily. All the binaries you can so all the 2-phase zones you can draw these tie lines, correct. So, that is what is shown in this picture here, very nicely drawn picture from the book, okay. Very nicely picture is been drawn from the book. So, you can see here that this is the 3-phase zone, 3-phase zone, 3-phase zone, and liquid is quite high here, but here actually temperatures are less. There are 5 temperatures instead of 6 I have shown you. In fact, T1 is a little lower. In T1 you can see alpha plus liquid, T1 is same as T2 actually. T2 is here the T1 whatever I have shown the board, then T2, T3 is exactly same what I have shown you. So, you have to basically replace T1 with T2, T1 will become T2, T2 will become T3, T3 will become T4, T4 will become T5, T5 will become T6, correct, and you get down to all these things very easily, fine. So, that is basically about the isothermal sections and the vertical sections. Now, let me go into the let me start, we will carry over in the next class also how to think, how to follow the solidification paths of these alloys. Little bit requires thinking process and also thinking in 3D space model. Let us suppose I have an alloy, composition is given by X and I want to see a solidification. How I will do? Well, initially alloy is sitting on the liquid, fully liquid. So, as it solidifies here, as you go to the next temperature, this is T2, T1 and T2. You see here liquid is it is in between liquid plus alpha. So, alpha will be forming because it is close to alpha. So, what is the way we do is that whatever is the closest phase field of solid phase, we connect a triangle. So, again this is the tie line. So, at T3 more amount of alpha will form, fine. Then finally what happened? Finally from there it will enter into the 3 phase field, alpha plus liquid plus beta, this is the point. Then you draw a tie line between alpha and like this is the tie line drawn. So, finally it is basically becoming like this and finally this is what is this. So, what does it happen? First it forms alpha, then form beta, because it will form alpha plus beta actually eutectic, and it will solidify at alpha plus beta eutectic. That is as usual, because this is an alloy which is not falling onto the eutectic, exactly on the eutectic. This is a little bit off eutectic composition, that is why. So, the way we follow is that this is the point and it goes on this liquidus at a temperature goes down, precipitating alpha with the composition alpha 2 given, and then at T3 more amount of alpha forms, the composition will be alpha 3. At T4 it moves into the, from this liquidus line it moves into the 3 phase between the line between the 2 phase liquid plus alpha and liquid plus alpha plus beta. So, the point is that as it hits that point it forms more amount of beta by eutectic reaction. So, eutectic precipitates forms more and more eutectic forms, more and more eutectic form, finally you have liquid alpha plus alpha is a dendrite and other one is eutectic between alpha plus beta. Okay. So, in the next class I will just discuss the 3D space model and tell you how it will follow. In fact, I need to draw the 3D space model on the board, that will take some time. So, before the beginning of the next class I will draw that space model and show you how this solidification will take place.